Hi, and welcome to Swerve 101, and this is our presenter, Jeremy Zhang.
Okay. Hello, everyone. I am Jeremy. So I'll be talking about pretty much all the mechanical aspects of designing a Swerve drive. But first, a little bit about me. If we could move to the intro slide. That's not the intro slide. Real quick, where is that? Where's the chat I meant? Oh, there it is. Okay. Okay, great. Okay, so a bit about me. I am a current senior on Stipulse, Team 694. This is my 4th year on the team, and I am Stipulse's CAD lead. I've also been developing a Swerve drive for 694 since 2018, and we were supposed to be an off-season Swerve this year. We had plans to build a robot, a mini Swerve bot for an off-season event, but well, pandemic happened. Okay. Next slide. Okay, so first some basic info. Okay, so what is Swerve drive? Very basically, you have your drivetrain divided into 4 modules, kind of like the one in the picture, versus a traditional tank drive where you'd have 1 gearbox per side. So the modules have a wheel on a pivot, and the wheels are both driven and steered independently. And what that allows you to do is your robot can move and rotate itself at the same time. Okay, next slide. Okay, so the pros and cons of Swerve drive. So Swerve drive is the most maneuverable drivetrain in FRC. Like no other drivetrain can, well, move and rotate at the same time. You've also got high traction and pushing power. So unlike a lot of the other omnidirectional drivetrains in FRC, you don't sacrifice those two things. The modules also make it, well, pretty modular. It's very easy to service a broken drivetrain. You just swap out the module, and because you can both drive and rotate at the same time, it allows you more design freedom with your robot because, well, any side of your robot can be the front side, so you can have mechanisms coming out of all 4 sides. Unlike tank drive, where you'd only really have mechanisms coming out of the front or back. So the cons, it's, well, definitely more expensive. There's no way around that. Swerve drive can also be potentially heavier, but more modern designs, especially ones that integrate a lot of 3D printing, specifically Markforged parts, can really cut down on weight to get you around where a tank drive would be. It's also significantly more complex than a tank drive, though COTS Swerve modules and example code both reduce the barrier to entry, both on the mechanical and programming front. It's very time consuming. If developing this takes at least 1 off season, and it also uses a lot of PDP slots, so 8 slots compared to 4 or 6 for a tank drive, which is pretty significant, and driver practice is mandatory. Like, you cannot skip driver practice with a Swerve drive. Okay. Next slide. Okay, so there's two main types of swerve drives floating around right now. So the most common one is coaxial, which means the drive and rotation basically are individually controlled by, so one motor, you have two motors on the module, one motor powers your drive and one motor powers your rotation, versus differential, where your drive and rotation are geared together in a sense. So both motors drive the wheel, and the difference in the speeds allows the wheel to rotate. And on the next slide, I have some examples. Okay, so the coaxial swerve would look like your module on the left. As you can see, there's one motor that the motor on the right drives the wheel, and the motor on the left drives a pulley that rotates that whole thing. But with a differential, you have something like the images on the right here. So on the rightmost image, you can see what the wheel module would look like. So you have those two gears, you have a little bevel gear inside, and you have a bevel gears on the faces of the two spur gears as well. So basically, when those two spur gears rotate at the same speed, it also means that the little bevel gear will rotate, and because those two spur gears are rotating at the same speed, that bevel gear doesn't go anywhere, and that means your module will drive forward. But let's say you wanted to rotate, you would speed up one of the top or bottom gears, which will cause the bevel gear to spin around and therefore rotate your wheel. So with a differential swerve drive, you have more power because, you have two motors driving your wheel versus just one, but it's also obscenely difficult to manufacture because it's very hard to get those bevel gears, and it's also incredibly difficult to program as well. So in this presentation, I'll mainly be talking about coaxial swerve drives because differential has never been on an actual FRC field as of this year. Okay, so next slide. Okay, and then lastly, a bit about COTS versus custom swerve. So there's plenty of good COTS options out there right now. Notably, 2910 sells a module, West Coast Product sells a module, ThriftyBot sells a module. There's a lot of good options. So COTS is great because, you don't have to design a module, but it's also more expensive than a custom option, and it's more difficult to integrate. So specifically, COTS modules are going to be bigger than custom options, and you're also not going to be able to control your ground clearance as well. Versus a custom module, which needs to be designed, but it's cheaper if you can manufacture everything in-house. You can make it significantly more compact than any COTS module on the market, and it's easier to integrate with the rest of your robot because you can flip the motors, so you have a lower module, and you have complete control over ground clearance. You can have whatever ground clearance you want, basically. Okay. Next. Okay, so now I'll be going over the most important design considerations for any module, which will be your motor choice, how you're rotating the wheel, how you're doing your bevel gears, encoders, and then lastly a bit about manufacturing. Okay. Next. So first off, motor choice. So for your drive motor, those are going to be your main options. So you have the sim or a mini sim, which is kind of the old school approach. All teams have been doing this for a decade at least. It's the tried and tested approach, but it's also big, heavy, inefficient, slow to accelerate. Overall, not the best option. So then you have the 775. This is kind of a more recent thing from a few years ago, but some teams do use 775s for drive motors because they are pretty powerful. So your 775s are going to be more compact than a sim or a mini sim, well, significantly more compact. They're also going to be lighter, and you still have comparable power, but you're going to need a larger reduction, which means more gear stages, which means more weight and more space, and, well, 775s burn. And you don't want to have your drivetrain burn out in the middle of the match. So, and now we have brushless motors like the Neo or Falcon, which are powerful, light, compact. You have a built-in encoder, but it's difficult to integrate an external encoder if you want to do that. Okay, next slide. So, and now a bit on the Neo versus the Falcon. So the Neo is going to be slightly smaller. You're going to have an external motor controller, and it's going to be a bit less powerful, but also pull a bit less current, versus the Falcon, which is going to be a bit larger, and it's going to have that integrated motor controller, but it's also more powerful at the cost of a bit more current, and it also has the Falcon also has the better integrated encoder as well. Okay. Next slide. So now that you have your drive motor, you're going to want to take a look at your turning motors. So for the gearing here, 200 RPM is a pretty good starting point. You typically want to gear about that fast, but you can go faster depending on motor choice. So so the first few options, I guess, that you have are the bag 775 and the brushed 550 class motors. So again, these are the old school approach. This just works, but it's also really tall because you're going to probably be using some planetary gearbox with this. It's going to be expensive because of said planetary gearbox, and, well, if you don't use the planetary gearbox, you're going to need a bunch of gear stages, so that's going to take up a lot of space. So then you have the Neo or Falcon, which is going to be a much more compact option than the bag or 775. It also standardizes parts if you're using the Neo or Falcon to drive as well. You're going to need a smaller reduction, but it's going to be a bit more difficult to integrate an external encoder. And lastly, you have the Neo 550, which is compact, and again, smaller reduction is needed than the Bagger 775, but again, it's also a bit more difficult to integrate encoders. Okay. And now a bit how you're actually going to rotate your wheel. Okay, so you can do that 3 ways: belts, gears, chain. So belts have the least backlash of the 3. They're also the least likely to slip, and they're the lightest option. Gears are kind of in the middle in terms of backlash, but you don't need it's a bit simpler because you don't need the precise center-to-center distances that you would for belts, but it can be heavy depending on, well, how big your gears are. And chain, you're going to have the most backlash. Chains can also slip, chains stretch, and it's heavy because you not only need the sprockets, but the weight of the chain as well. Chain is overall not great. And backlash, it just means that, well, nothing, like no 2 gears, belts, etc. will mesh perfectly, and the extra bit of slop between the teeth is called backlash, and that's important to mitigate because having a bunch of backlash in your module will mess with how precisely you can control it, and you're going to want this thing to be as precise as possible. Okay. So now on to how you're going to set up your bevel gears. So once again, there's 2 main approaches. The first one, well, at least nowadays, is much more common. So you have a bevel beside wheel setup means you have your bevel gear on the same shaft as your wheel, and usually there's a not 1-to-1 reduction, so like a 3 or 4-to-1 usually. This approach is more compact, but buying those bevel gear sets can be kind of expensive. Your other option is to have an additional gear reduction after your bevel gears. So basically you'd have a set of 1-to-1 bevel gears and then some additional gear, chain, or belt reduction. So this is a bit cheaper and it's easier to procure because you can just get 1-to-1 bevel gears off of Vex. Those work pretty well instead of going through some, I don't know, Chinese supplier, KHK, etc. But this is also much, much less compact than a bevel beside wheel setup. Okay. Next, and now the last bit before I talk about before I look at a few teams and how they design their Swerve drives is how you're going to support your drive shaft. So there's two main approaches. You can use some bushing or bearing setup. So the bushing, so you're going to have a metal hub, the image on the right, that rotates inside of a plastic bushing like the image on the left, and your pulley, gear, or whatever that's actually going to rotate the module is going to bolt into that hub, and your drive shaft is going to be running through that hub on bearings. So this is going to be pretty durable. It's cheaper than your bearing because, well, all you're really paying for is just the stock that you'd use to make these parts. But at the same time, it's not the most compact solution. Whereas if you use a large thrust bearing like the picture, it's going to be, well, essentially indestructible in terms of FRC stuff, but it's going to be a bit more expensive but at the same time much more compact. Okay. So the first module we'll be taking a look at is Team 2767 Strike Force. So here they do the bushing thing. So you can see a bushing with that metal hub inside that bolts into the pulley. And inside the hub, there are two bearings to constrain the drive shaft. So they're using 775s to rotate and drive the wheel, to drive and rotate the module, sorry. They're also using a bevel beside wheel setup, as you can see. So this is going to be pretty compact, but at the same time, it's going to be kind of difficult to manufacture because, well, Strikeforce really likes their Markforged parts. A lot of the gearboxes, the pulleys, the wheel forks are made on it. They're Markforged. They also weld their bevel gears to their drive shaft, so if you can't weld, you obviously can't do that. And it's also going to be pretty tall because of the planetary gearbox that they use for their 775. Okay. Next slide. So now we have 2910. 2910 uses a large thrust bearing that their pulley fits inside. They're using both Neos to both drive and rotate, and they have the same bevel beside wheel setup. So something like this with the giant pulley, gear, whatever, that slips inside of that thrust bearing is currently the most common design out there. So and it's rightfully so because, well, it's very compact. It's, well, overall simpler than at least in my opinion, than what Strikeforce does. And it's very robust. This thing has survived dropping off level 2 every match in a season from last year's game. It also survived the rendezvous point from this year's game. This thing isn't going to break, but this is still going to be difficult to manufacture because of all the machine parts that you need, and it's going to be expensive if you're just buying it straight from 2910. Next slide. Okay, so now we have 254's off-season module that they fielded in 2019. This is kind of an extension of 2910, to be honest. I mainly threw this in here to showcase the upside-down motors. So you can't really see it. Well, you kind of can, but they're running the same 2910 style pulley and bearing setup. They're using mini sims instead of neos for drive and rotation, and again, you can't really see it, but they have the same bevel beside wheel setup that 2910 does. So the reason why they flipped their motors is because, well, at least in 2019 specifically, there was that little cutout in the cargo ship for your bumpers, and if your motors were above your bumpers and you rammed into that thing, the cutout could destroy your motors. 2910 had specifically had a lot of issues with that at their first event. And also the flipped motors allows their 254's giant turret arm thing to clear their modules, so they didn't have to worry about that thing hitting their modules and potentially breaking something. But this is, again, going to be a pain to manufacture because of the pocketed parts, that, as well as what I think are 3D printed pulleys, but I'm not sure on that. And the downside of the flip motors as well is that it's going to be bigger than alternative module designs. And lastly, we have 1533. They do something pretty unique in that they have they actually make a custom bearing. They 3D print that, and they have a custom gear that fits inside. They're also using versaplanetaries as for gearboxes. They have a Neo for drive and a Neo 550 for rotation. This is an old picture, so it shows 775s, but that's what they ran this year. And as you can see, they have the 1-to-1 Vex bevel gears and an additional gear reduction after that to drive the wheel. So the good thing about this is, between the versaplanetaries and the two gears, you can very easily change your drive reduction and your rotation reduction. But again, because of the versaplanetaries, it's going to be a lot taller than the other modules, and it's going to be very complex in terms of both design and machining because of, again, that whole wheel assembly is going to be pretty hard to make, and the bearing as well. That's going to be pretty difficult to design and manufacture. Okay. So now a bit about encoders. So encoders are necessary. So an external encoder is necessary to control your module rotation, and if that fails, so does the rest of your Swerve drive. So pretty important. Okay. So the important one here is your turning encoder. For your drive encoder, you can pretty much just get away with the integrated encoder on a brushless motor if you're using those. Or if you're still using sims, you can just throw a sim coder on there. But your turning encoder has to be an external thing that's geared 1-to-1 with the rotation of your module. And it should also be an absolute encoder because absolute encoders can remember their zero position versus an incremental encoder where the zero position resets every time you turn your robot off and on again. So you're going to want to remember that zero position because it'll simplify your code a bit, and it takes an item off of your pre-match checklist. So if you're using that incremental encoder, you're going to need some reference, so like a limit switch, for example, as a zero, or you're going to have to rotate your module to its zero position every match, basically, and if you forget that, basically your robot breaks and is unusable for a whole match. So yeah, don't use an absolute encoder. And the reason it should be geared one-to-one as well is, well, because of that zero position specifically. You have to know where the zero position is, and if it's not geared one-to-one, let's say 2-to-1, there's going to be multiple positions where the module can supposedly be zero. And yeah, that's just not going to work. Okay, so some good options for your turning encoder include the CTRE's mag encoder or the versaplanetary encoder if you're using versaplanetaries. You can also use the MA3 encoder that AndyMark sells, like the one in the picture. And recently there's also the Lamprey hollow-bore encoder. And that's great because you can make your module really compact. A lot of designs using the Lamprey have gotten modules down to like 4 inches by 4 inches, which is pretty crazy, but there's a bunch of issues with it. So if you want to use it if you want to plug it into a Talon or a SparkMax, for example, you're going to need to jump through a bunch of hoops to get it to work. So you're going to have to like remove a bunch of pins on the connector to prevent it from randomly re-zeroing. And you're going to have to use a breakout board if you want to get it to connect to the SparkMax. So overall, it's kind of a weird option. So it has potential, but there's a bunch of issues with it. Okay, next slide. And lastly, I'll be going over some manufacturing stuff. Okay, so this will just be some very basic tips and good practices, I guess. So you're going to want to cut down on manufacturing time wherever possible. So because you don't want to spend like 3 weeks just machining your drivetrain, you're not going to have time for the rest of your robot. I mean, that's less of an issue now with no bag, but say you're competing week 1 or week 2, you're not going to want a half-finished robot. So when you're designing parts, you want to first make sure you can make it, and then your next priority is making the thing as robust as possible, because the last mechanism you want breaking is your drivetrain. It's the first, second, and third most important mechanism on your robot. So you do not want that going wrong during a match. And after you've made sure that your parts won't break, then you can focus on making it lighter. So you're going to want to minimize the number of unique parts you have, just to again speed up manufacturing. COTS parts are good if you can use them. You're going to want to use 3D printing extensively if you're designing a custom module, because it saves a significant amount of weight. So your best option is Onyx if you have access to Markforged printers. So it's very light, and well, this isn't me, this is Markforged marketing department. According to them, it's a drop-in replacement for aluminum. In reality, it's not, but it's still incredibly strong. But even if you don't have access to that, you can get away with ABS, PETG, nylon, even PLA if you design it right. you can still have very strong parts while keeping things lightweight. Okay. And just to conclude, so just the most important takeaways, I guess. So the drive shaft on your Swerve module must be properly supported, because if it isn't, it's going to bend and you're going to end up with 4 broken modules and a robot that can't drive. So and there's plenty of good ways to do that. Just, well, pick one of those and yeah. So your module is going to have to be robust. You don't want this thing breaking during a match. And then you're going to want to make this thing as simple as possible, and then after that you can start worrying about how light or compact it is. Encoders are extremely important. Again, your manufacturing capabilities are important as well, and because, well, if you can't if you can't actually make your module, you're going to want to either use a COTS option or not do it entirely. Developing Swerve is very time consuming. It's, again, at least 1 off-season, multiple if necessary. And, well, sometimes a COTS module is the best option. You don't have to design some crazy custom module to field a great Swerve drive. There's a lot of very good COTS options out there that you can absolutely use. And okay. So here's a bunch of resources that I thought I'd compile. So Strikeforce over the years has released this very extensive document that just goes over their entire history with Swerve Drive, their design process, and all that. It's pretty enlightening. Chief Delphi in general is also a great resource. There's a lot of interesting designs floating around out there with CAD files if you want to poke around at those. 1640 has a similar extensive database on Swerve Drive. You also have that white paper at the link for code stuff, and 2910 releases their example code. I believe you can find it on Chief Delphi or on the Swerve Drive Specialties website. Okay. And yeah, that about sums things up. Okay. Are there any questions in chat?
If anyone has any questions, feel free to put them in the chat. Not just to get us started. Jeremy, what do you think is the best option for a team looking to start with Swerve Drive, like COTS or custom?
In my opinion, well, right now, you should absolutely go with one of the many COTS options out there. So COTS options are pretty great. 2910 and the West Coast Products module are both, well, nearly indestructible, and they're pretty compact. It's going to be pretty difficult to design something that's smaller and lighter than those if you're just starting out with Swerve Drive. And also the module that the Thrifty Bot sells is also, well, $200 without motors or motor controllers. It's going to be pretty hard to undercut that on price if you're just doing this first year. And so, yeah, COTS is probably the better option. Once you've done that for maybe a year or two, you can start thinking about custom, but you can go pretty far with COTS modules these days.
Awesome, thank you. And on top of that, how would you go about designing a Swerve module?
Okay. In my opinion, the best design is, well, what 2910 does with that bearing. there's a reason why it's the most popular design out there. It's it's very compact. It's very durable. It can be light. If we could go back to the picture I had up. Yeah, that's actually the module that 694 was planning on using. It's very similar to what 2910 does. So basically, I don't want to say copy, but like do the same bearing and thrust bearing and bevel beside wheel setup that 2910 does, and yeah, pretty much.
Just another reminder, if anyone has any questions, feel free to put them in the chat. Oh, are there any good practices for training new drivers in Swerve?
New drivers. So this is kind of a programming thing, but how Swerve drives are coded nowadays is, well, you have this thing called field-oriented drive, which means pressing. I have a controller right here. Pressing forward on your controller means your robot will always go down the field away from you, regardless of whichever direction your robot's facing. Backwards, it'll come towards you, left, right, etc. And that is well, from what I've heard at least, pretty easy to drive. If you want to practice without an actual Swerve drive bot, because well, obviously the best option is to just put 4 modules on a test chassis and drive that around. But if you can't do that, the FRC simulator that team 11115 FTC team released, that their field-oriented mechanism drive is a pretty good approximation of what a Swerve drive would feel like to drive. So if you don't have access to an actual robot, you can just practice with that.
Awesome. Great question. Are there any more? It looks like that is it on questions. If anyone has any more questions, feel free to put them in the chat. If not, I believe we can adjourn unless anyone has any questions or Jeremy has anything you would like to add. I believe we can stop. Yeah, I think, I think that's it. Just a reminder, please fill out the survey that Mr. Solomon put in the chat. And thank you everyone for coming here. And if you have any questions in the future, I believe Jeremy would love to answer them if you email to